Hi everyone. My name is Mitch, and as Tim said, I'll be taking you through the Shavetable 2 system, which you should be seeing on a webcam here. So this is the complete solution that you view on your screen. So I'll just be going through a bit of the hardware of the Shavetable 2. But before that, I just want to say the Shavetable 2, because these are the common questions that usually get asked. This is basically the specification breakdown of the Shavetable 2. It's rated to accelerate a payload of 7.5 kilograms at 16.5 pounds at 2.5 G. So that's the rated acceleration. It can handle a lot more payload. For example, you can put 60 pounds on there, no problem, but the acceleration would be decreased. And we have graphs and stuff like that we can generate that, based on the load you have, how much can you accelerate it, and so on. The stage stroke, so if I go down here, so the stage, I'll just be moving manually, has a stroke of plus minus 3 inches. So plus or minus 7.62 centimeters. So that's the stroke that you have. The next item is the bandwidth. The bandwidth can comfortably go to 10 hertz. At small amplitudes, we can attain 20 hertz. So those are the top 3 specifications we get asked. So now I'll be going through the actual hardware of the Shavetable 2. Mind you, this is a demo system, but the hardware is no different. So we have a 400-watt 3-phase motor right here. So it's a very powerful system and it's ball screw actuated, so very robust. It's riding on 2 ground-hardened shafts, as we show here. In terms of sensors, we have an accelerometer that's mounted right here underneath the table. So it's an XY accelerometer that we manufacture. We have an encoder that's embedded inside the motor. So the encoder gives you position feedback. And I believe the resolution is about 3.1 micrometers. So very high, very accurate position measurement. Next are the limit switches. So there are 3 limit switches on the table. And if I take this to the left, then that will trigger a left proximity switch or limit switch. There's a home. The home is the center stroke position. And then we have the right. So 3 limit switches. And those are used for 2 reasons. They're used in normal operation. They're used for safety measures. So if you hit the left or right limit for some reason, then it will deactivate the amplifier. The home is used for calibration purposes and so on. So in calibration, when you're in calibration mode, the rules are a bit different. Now it uses the left and right limit switches to calibrate, which we'll see later on. So that's basically what's on the Shavetable system. Here is an optional, I'll take you with the amplifier. So the blue box here is the power amplifier for the Shavetable 2 system. So it's called a UPM 18025B. It's a PWM based amplifier capable of supplying up to 25 amps peak, 12.5 amps continuous. It has an embedded PIC inside of it, so that's what does the disabling if it encounters a limit. There's an e-stop, an emergency switch. So this is a switch that the operator can use nearby the PC. So again, you can slam this down in case of any issues. So it does have that other layer of safety. And very easy connections. So there's only 2 connections that go to the table, and then you have an accelerometer connection, and so on. In order to interface to this equipment, we have a data acquisition card on the computer. So the data card on the computer, it's a Q8 8-channel data acquisition device. And there's a terminal board that's actually especially made for this amplifier. So the only cable you really need that goes to the Shavetable is only 1 cable. So you just have a serial cable, a parallel cable that goes between the data card on the PC to the amplifier here. So connections, although it may look like it's extensive, it's actually the connections are fairly simple for the system. The next item that we'll go to later on in our presentation is the AMD. This stands for the Active Mass Damper. So the active mass damper is a flexible structure. It also has an accelerometer, so you can measure the accelerations of the floor. You can also have a cart, an optional cart, to make this into a smart structure and try to dampen the motions of the building. So that's pretty much the solution. There's two software options to run this. So when you've completed the setup of the system, there's two options to run the system. There's we have a Shaketable 2 software, which is standalone. The only thing you need is LabVIEW runtime and our Quark software. I'll talk about Quark later on, but that's the easiest way to get up and started. And so I'll demo that first. I'll show you the Shaketable 2 software and what you can do with it and what you can't do with it. The next step is I'll introduce you to the MATLAB Simulink solution we have to run the table. And also, while I'm on the subject, we are going to be releasing a LabVIEW software approach for the Shaketable 2 as well. All right, so let's begin with the first software option, which is the Shaketable 2 software. So I'm just going to load this up. So it's just an icon you have here called Shaketable 2 software. If I double click on it, then it launches this graphical interface. So it automatically calibrates the system. By that I mean it automatically homes the system for you. So that's just another step that makes it easier. As you can see, I can change the amplitude and the frequency of the sine wave. So I can decrease it and then start increasing the frequency, for example, to 2 Hertz. And all things are done in real time, where I can increase the amplitude. So these are things you can do as you're running the system. This is the position I'm being shown, so it's showing the desired and the measured position. You can change the scale, the scopes, and so on. We also have the acceleration measurements of the table and as well of any other accelerometers connected, including the structure. So the blue line here will be showing the acceleration of the table. So if I increase this a bit to like 2 Hertz or something, then you'll see increase that. And you'll see that the acceleration of the top stage in red increases as well. So if I decrease the frequency, it goes down. All signal transitions are transitional. So now if I change it to a chirp or a sine sweep, very common to find a natural frequency of the building, for example. And this would show you, and then it restarts. We also have, we have sine wave, we have chirp, we also have 4 precompiled earthquakes. So the, for example, Northridge. Okay, so now I went, this is, just restart that. So see, it calibrates it, makes it home, and then it'll fire up the Northridge system. So that's an example of an earthquake that's scaled down and fitted for the table. And if I go back to sine wave, then again, it'll make the smooth transition to the new signal and switch it off. And then I can click on stop, and the system's in your lab is done. So a couple of things here. If you do have LabVIEW on your system, then you can export this into Excel. So I can click on the position here and say export data to Excel, and it'll automatically just put it over to an Excel sheet. So then you can use all this data here, for example, and say, insert a line graph, and it'll show the time. So just delete the time here, and then see this shows you the data. So you can save data in Excel very easily if you have LabVIEW installed, the full LabVIEW version. I don't think it does it with LabVIEW runtime only, but anyway, that's something to consider.
So this is, like I said, it does everything for you. Initializes the amplifier, it centers the stage, and it's easy to command different signals. What it can't do is, you can't add new earthquake simulations, you can't modify signals, and so on. So it's not, it's a closed architecture type software. Now, if you want to do some modifications and stuff, that's where the MATLAB Simulink Quark solution comes in. Which is what I'll show next. But yeah, so that is the Shapetable 2 software. So I'm just going to close that, and then I'll show you the second method. So this method is all based on MATLAB Simulink. Now I've trained a lot of people on the Shapetable system, and I find it's pretty much 50-50. Not everybody uses MATLAB Simulink. So it's very, I guess it depends on it just depends on the institution. So if you haven't seen it before, then it might be a bit much, but I'll go slowly. And hopefully, but most of the controllers here are running in Quark, so you don't need to know too much about MATLAB Simulink at the moment, but at least this will be an intro to you, so I'll try to give you a bit of a primer as I'm doing this, because I am aware that some people don't use it that much. So I'll just start over with the MATLAB Simulink. So in option 1, we saw the software, so now I will show the MATLAB Simulink solution. And as I was saying, some of you might have been cut off with the audio. I'm aware that some of you may not be familiar with MATLAB Simulink, but that's fine. I'll try to do my best to give you a bit of a primer as I'm doing this. But basically, MATLAB is a text-based mathematical language. You can do some programming and stuff like that. It's very, very great for doing data analysis. And Simulink is, as I'll show, our block diagrams, and we use Simulink to run the Shapetable. So all this will be evident as I go. So the first step before you run any of our Shapetable controllers is the setup.m script. So if I open this up, this is supplied with the Shapetable system, and it sets up all the variables for you. So if I run it, then I'll ask you, okay, do you have any additional load on top stage? We have nothing significant, so I'll just enter 0. And then I'll list some data like some data like the mass, the preload mass, and the limits, and the max load acceleration based on the load you entered, for example. If I click on yes here, if you want to view the set point limitations, so by set point limitation, that means basically it's the bandwidth, right? So the bandwidth based on the payload, what position can it command, and at what frequency for a sine wave. So if I maximize this, then it shows you what acceleration you reach depending on the command you give. So the blue line is the limits for the position, the red line is the limit for the velocity, and the green line is the acceleration limit. So I'll just maximize this again. So for example, if you want to reach 1G, then for signal at 4 Hertz, we need this kind of amplitude. We need a sine wave about a bit above 20 millimeters to reach that acceleration. But so I don't need that right now. So now my workspace, my MATLAB workspace has been set up, so I can go and get this ready. So the first thing you want to do is center the table, otherwise known as calibration. So this is Simulink. So this is the Simulink, the block diagrams that we use. So again, all these files are supplied with the Shapetable system. And the nice thing about this is, if I double click on here, this shows you these blocks here are actually made by us. So this is part of the Quark software. So Quark works with Simulink. It's quite seamless, but what Quark does is we add some blocks to interface to our hardware, but it also allows you to generate code from the Simulink diagram and run hardware. So those are 2 key things that Quark does. Simulink is a great environment for modifying controllers because it's all it's more concept based and all that. So if you want to change the signals, it's quite easy to do it in this platform. But for now, let me just show you how you would calibrate the table, how you would center it using this approach. So the first thing you gotta do is you go to the Quark menu. This is another thing that gets installed automatically once you have Quark set up on your system. So you go to Quark and build. So what that does is it generates real-time code from your Simulink diagram. You'll see in the MATLAB prompt here, generating code, and it'll go through the different prompts, and at the end it'll say downloaded controller. So it's finished compiling, and there. So model QCal has been downloaded, and now we can run the controller. Because right now it's not actually home, so I can go connect to target and start, and then I'll go over here and center the table for me, and then I'll prompt a message saying calibration complete, and so that's good. If you didn't do that and you try running another, like the sine wave controller, it will prompt you to say, hey, make sure you center your stage before running this controller. So it has all these safety measures embedded inside. So let's open QSine. So we saw, so this commands a sine wave to the stage. So this is handy for, for different reasons, right? Because most people want to supply a sine wave. But again, so the sine wave in here, if I double click, here's a sine wave. So you can easily change that to say a square wave. If I go here and I say square or triangle, then you could do that. And of course, we would have to change the amplitude and the frequency of that different signal. But just giving you, just showing you how easy it would be. So I've already built this controller already. I've already generated the code, so I can just go Quark and start. And there we go. So just like in the software, I can go ahead and change my amplitude to 1.5. Or I can change it to back to 1. Change the frequency. So all the same stuff I've done in the software, I can do through this, but it's a different interface, and you have that capability of modifying the diagram if you want. The other thing is also you have scope. So here I'm measuring the position. This is the acceleration of the tables. This shows the acceleration. It's pretty low right now, so it's not showing you a great amount. And then when you want to stop the controller, you just simply click on stop. So that's the sine wave. So I'm going to click that. I won't save. Now the next one. So we've already kind of touched on these different controllers. The next thing I want to show is actually, I'd like to show how because you can save data in MATLAB. And as I was saying, you know what, actually I will probably save that until later. Right now, maybe I'll show you the earthquake and how you can simulate different earthquakes. So inside, we have a diagram called Q earthquake. So Q earthquake, remember the sine wave. The sine wave here had a sine wave command, but in here we supply earthquake data. And this is how you would do it. So you could log on to, for example, like all this information, all this data. So as you can see here, for example, NGA number, these are all acceleration records that we've downloaded from PureStrong Motion website. So what you do is you go to this website here, Pure Ground Motion Database, and you would download an unscaled acceleration record from a certain earthquake that was recorded at a certain station. You download that and you get a file sort of like this. So this is the file that has a certain format. All the accelerations are in gravitational units. So this is an actual record, for example, of Northridge taken at this station here, or Sylmar Hospital. Now, this earthquake record has large displacements. The shake table has a limited displacement of plus minus 3 inches. So we need to scale down the system to a certain the displacement of the table. So the way you can do that is using this here, the make quake. So make quake here, if I run this, I'll just run it right now. So if I run it, so here I've selected the Northridge, so input file name, I've inputted the acceleration record that I downloaded. So SIL090, this is the Northridge earthquake that I showed you on the website. So you input the file name, and then you enter what is the maximum displacement you want. In this case, I put 1.5 centimeters. You could go more than that, because I mean, you could go up to 3 or 3.5 centimeters if you wanted to. But right now, I'll just limit it to 1.5. And after you run it, you get this graph here. So this graph shows you the earthquake acceleration that was recorded and the earthquake position. So note here that the centimeters go up to 15 and 20 centimeters for this. So very large displacement. The graphs on the right, so the graphs on the right here shows you the table acceleration expected as well as the table position. So note, let's look on the bottom right here. The table position is scaled down to 1.5 centimeter, the x parameter that I specified. So it's scaled down to 1.5 centimeter. However, if you note on the top right graph, the table acceleration is maintained. It's the same as the earthquake acceleration. So what this Quantzer Q-scale algorithm does is it shrinks down the displacement. So it calculates a scaled displacement for the table to track in order to maintain the same acceleration. So it does that basically by shrinking the time. So your record doesn't last as long because the time is shrunken, but the acceleration is maintained, and but the displacement is reduced. So I'll close down that graph. I'll close down this. Go back to my diagram, and I'll just go ahead and start system. So there we go. So this shows you the Northridge. And then control and finish. So it automatically stops. So it automatically stops after the control is done. Now let me show you an example. Let's say I want to change the displacement to 2.5, and I want to use a different earthquake. So I would go this earthquake here that I downloaded again from Pier, and I would run it. There we go. So that's a different record. So let's run this guy instead. So because it's a different set of data that I've loaded, I need to rebuild my controller. So I need to go back to Corp and say build. Because something significant has changed, then you need to rebuild it, but subsequent builds don't take very long. There, so we're done. Then I can go Corp and start. There you go. So it follows, it tracks that position, and then you get the measured acceleration here. And acceleration. So that's an example of how you can simulate different earthquakes using the Q scale and the Q earthquake. So that's something very common that people want to do. Now the other thing that we can also do is save large amounts of data in MATLAB. So if you want to calculate, for example, the FFT to find the natural frequency of the building. So let's try to do more of a focused example. So I'll go to QSweep. QSweep will feed a sine wave. And if I go to accelerations here, I'm actually saving, you'll see here, A1 stands for floor 1 acceleration in G. So I've got a little block that, again, this is a Quark block, and it saves all the acceleration data of the floor to a type of file called MAT, a MAT file. So that's a MATLAB data file, and it's really good for, it's basically like a spreadsheet. It saves good for saving large amounts of data. So during the whole course of this controller, it's going to save the acceleration data to this file, and then I can use that for offline analysis. For example, to find the natural frequency. So let's run this guy. So the sine sweep, I believe, goes from up to 10 hertz. So it goes from 1 to 10 hertz. And then it automatically stops. Just to verify, I can go to my block here. So go to sine sweep command and the chirp here. Yeah, so it goes from 1 to 10 hertz. So that way, so I've ran all this. Here's the acceleration of the table. Here's the acceleration measured of the AMD, the first floor. So all of this has been saved. So all I got to do, again, these are files that we make. So what's good about MATLAB is you have a command called FFT that does all the computation for you. You got a bit of nostalgia to do, but not very much. So this is a script that we supply. You just supply the data file for the acceleration data file in here, the min and max frequencies you've used, and the sampling rate of the controller, which is actually 500 hertz, by the way. All these controllers are running at 500 hertz. You could boost them up to 1 kilohertz or even 5 kilohertz if you wanted to, but for our purposes, 500 hertz is plenty. There, so if I run this guy, it shows you the FFT. So you can see the peak here. Here's my natural frequency. So I can close this, just to zoom up. So you can see it's about at a little over 2 hertz, or 2.5, a bit less. Now it is a bit on the higher side because I had my structure on there, and the structure wasn't tied down. By the structure, I mean, sorry, the cart. So the cart was allowed to freely move, and that actually adds passive damping to the system. So if I ran this again, and actually constricted the position, so what I'll do here is I'll try to actually, so if I bring this up here, just tie it down. I'm just going to use a twist tie. Yeah, I won't hold it. I'll hold it a bit, but yeah. So I just want to constrict the position slightly and rerun it. And then we can see the effect of it again. We should see a change, but there. So now you can see the cart was moving less, so that should change the profile of the building. Okay, there we go. It's done. So now I'm going to go back to MATLAB. I'll rerun the script here. So I'll open this, run it. See? So now the frequency is a little bit different. So it's dropped down just slightly, maybe 0.1 or 0.2 hertz. So there's an example of easily finding the natural frequency of the building. It's something that's commonly done in like structural dynamics, for example. Yeah, so remember that value. We got about 2.2 or something. So that will come in handy later. So for this, the last demo I'll be doing is with the active mass damper system. So now, so we haven't actuated the cart at all. We haven't been using the cart yet. So in this one here, again, I'm going to run the setup script, and I'm going to load up the assembly diagram. So the assembly diagram here is
is for using the Shaketable 2 system with our active mass damper. We have different types of mass dampers, by the way, our smart structure. So I can remove this now. So we remove we have the 1 floor and we have the 2 floor. So of course this is the 1 floor AMD. So now what I'm going to show you is the difference of having no active compensation and having it on, what the differences are. So I'll start running this controller. So right now it's going to be on passive mode. So what I mean by passive mode is the cart is locked into the center position right now. So this is, again, with no damping, and as before, I can go ahead and change the frequency of the sine wave of the table. So in the bottom half of my screen here, this is my Shaketable control. So if I increase the frequency of my sine wave to closer to the natural frequency I had, right, which is like 2 point something, but if I go like 1.95, you can see the acceleration is quite high. So right now I got acceleration of about almost 1 G. So yeah, I've reached 1 G. So I'm just going to change the scales here, for example. And I'm just going to close some stuff down. So the primary things we're looking at here is this here. So this is acceleration of the top floor. So again, if I go back to 1.95, this is getting close to natural frequency, right? So note this value and note how much it's moving on the webcam. So I'm going to bring it down to 1.6, and now I'm going to activate the cart. So when I activate the cart, now you see the cart moving back and forth. So now it's actively trying to compensate for the motions of the structure. Let's go back to 2 Hertz. So now the acceleration is attenuated by about half. Like we were reaching almost 1, and now we're down to about 0.4. If I go like 1.9 and I turn it off, you'll see the difference right away. If this one is off, you try, you might be able to do it dynamically, but sometimes, there we go. So you can see the difference there. It's off and on. I'll just stop that. So the way it does that, so I had some other scopes here that I want to show you. So this is the position of the cart, and this is the estimated position of the cart, because you can't have it. Of the floor. So this here is actually is an observer that estimates what the displacement is of the top floor. It does that by using the cart position and acceleration of the floor, as well as acceleration of the base of the Shaketable. So by using those 3 signals, as well as the voltage being applied to the cart, you can estimate what the displacement is of the top floor. And using that estimation, that gets fed back to a closed loop controller on the cart, and then it tries to dampen, it tries to minimize or mitigate that position that's estimated. So by trying to regulate that position down to 0, you effectively attenuate the acceleration. So that is basically the logic or the algorithm behind the active mass damper system. Now I've seen some other, so this is one way to do it, like the smart structure with active compensation. Of course, in a lot of buildings, it's usually using passive compensation. So I have seen some people
that, for example, run a sine sweep without the cart, without anything, just a structure. And then they would mount a pendulum, a heavy pendulum, and then run the same signal through the table, and then students can observe the effect of the acceleration change and stuff like that. So I have seen that as well in some universities. Okay, so that concludes most of all of the Straight Table 2 demos that I want to give. The only thing I want to leave off with is, so this is one solution, the Straight Table 2. We do have other tables. So the Straight Table 2 is our most popular product, but we also have this. It's called the Straight Table 1-40. The -40 stands for the stroke. So this one goes plus or minus 20 millimeters. It's spec for moving a 1.5 kilogram payload at 1 G. So it's our most portable. This is our most portable solution. You can also mount an AMD on it as well. So you can definitely mount an AMD just like we have on right now and conduct the same experiments. It's just you have a bit less stroke and less power on the system, but it's more portable. And you can connect it to a laptop if you wanted to, because it doesn't use the larger amplifier, Blue amplifier, so you can run this off a laptop. So that's on the benchtop side. We have the Straight Table 2, and then we have the Straight Table 3. So the Straight Table 3 looks like this. So this one is a dual axis system. It runs on linear motors. So Straight Table 2 is ball screw. This is linear motors. It also has very high accuracy encoders, an accelerometer. And this is usually used more for advanced teaching and research, or if you have larger structures. It's spec to move 100 kilograms at 1 G. And the stroke is 10.9 centimeters, so a larger stroke as well. So this is a very, very nice system. Last remark is you can actually mount two Straight Table 2 systems perpendicularly to have XY motion. So you can have one Straight Table 2, mount on another Straight Table 2, and have XY motion. So that's another solution that people have used as well, and we have full compatibility, full support software and documentation for that configuration.